Hello everyone! In this lesson, we will learn together about the process flow of secondary brine purification, including a brief overview of the secondary brine purification the process flow of secondary brine purification, the impact of process parameters on resin tower operation, and the control parameters for secondary brine purification. A brief overview of secondary brine purification process. Add refined hydrochloric acid to qualified primary brine to adjust its pH value to between 8.5 and 9.5, aiming to dissolve the suspended solids in the brine. Then, the brine is preheated to 55 to 65 degrees Celsius and sent to the chelating resin tower. In the resin tower, the brine contacts the chelating resin from top to bottom for ion exchange, ensuring that the total content of calcium and magnesium ions in the brine exiting the resin tower does not exceed 20 micrograms per liter. There are generally two types of purification processes: 3-tower process and 2-tower process. 3-tower process, towers A, B, C under normal circumstances. 2 towers are connected in series for online operation, and 1 tower is offline for regeneration or waiting, with the operation mode repeating 3 steps. 2-tower process, towers A, B under normal circumstances. 2 towers are connected in series for online operation. Then, 1 tower runs online and the other is offline for regeneration, with the operation mode repeating 3 steps. As can be seen from the 3-tower process work step table, the 3-tower process requires a slightly larger one-time investment, but provides much more reliable control over brine quality compared to the 2-tower process. 2. Process flow of secondary brine purification. 1. 3-tower process flow of secondary brine purification. The process flow is shown in the figure. In a typical flow, there are 2 processes: pure water replacement process and the air purging dispersion process. The diagrams show the pure water replacement process flow and the air purging dispersion process flow respectively. Improved air replacement process flow. This process features stable operation, simple equipment, and savings in pure water and brine, with specific advantages as follows. Compressed air uses existing process pipelines to enter the chelating resin tower through the upper and lower nozzles. The upper nozzle via a gas distributor, removing refined brine and regeneration acid-alkali from the tower, replacing the original pure water and significantly reducing pure water consumption. Compressed air replaces large flow pure water for backwashing to loosen the resin, achieving better results and improving resin regeneration efficiency during acid and alkali regeneration. Compressed air is introduced through the lower nozzle of the tower for turbulent mixing, making regeneration more thorough and solving the problem of incomplete resin regeneration. Compressed air replaces pure water for drainage, allowing refined brine during the regeneration cycle to directly enter the refined brine tank without generating recycled dilute brine, reducing energy consumption, minimizing acid-alkali wastewater discharge, and lowering process costs. 2. Adsorption process, flow of chelating resin towers. The adsorption production process of resin towers is divided into 3-tower process and 2-tower process. 3-tower process, 2 towers are always connected in series for operation, e.g. A in series with B, B in series with C, C in series with A, and 1 tower is regenerated with short waiting operation cycle, frequent regeneration, and high safety factor. 2-tower process, 1 tower is regenerated and 1 tower is in operation, detailed as follows. Specific steps of the 2-tower process. The primary brine, after membrane filtration, is first preheated to approximately 60 degrees Celsius with chlorine gas produced by electrolysis. Then enters the resin tower. A flow control valve FV is installed before the primary brine enters the chlorine-brine heat exchanger, allowing control of the brine flow rate into the resin tower. Via DCS2, towers operate in series. The first tower removes most calcium, magnesium, and other metal ions, and the last tower acts as a safety tower to ensure ion content meets standards. The entire chelating resin adsorption unit is automatically controlled by PLC or DCS, with status signals of on-site instrument, valves fed back to DCS for monitoring. The secondary brine is sent to the refined brine buffer tank, then pumped into the refined brine high-level tank, and finally delivered to each ion membrane electrolyzer. Resin tower regeneration process discharge the brine in the tower, replace residual brine with pure water, and rinse broken resin, flush brine into the tower. Then introduce pure water from the bottom for backwashing to remove broken resin and loosen the resin bed, and then discharge the liquid in the tower. Inject proportioned hydrochloric acid to convert the resin adsorbed with metal ions into hydrogen, form resin. Add pure water to replace the acidic solution in the tower. Then inject proportioned alkali solution to convert the hydrogen form resin into sodium form resin. Replace the alkali solution in the tower with pure water and flush away the resin broken due to repeated expansion and contraction. High impact of process parameters on resin tower operation. In addition to its own characteristics, the absorption capacity of chelating resin is affected by factors such as brine temperature, pH value, flow rate, calcium, and magnesium ion content, and free chlorine, which need to be strictly controlled to ensure the quality of brine entering the electrolyzer. Temperature. The chelation reaction is carried out at a certain temperature. The higher the temperature, the faster the reaction and the longer the resin service life. However, when the temperature exceeds 80 degrees Celsius, the rising strength decreases, the breakage rate increases, and the resin is irreversibly damaged. Control range 55 to 65 degrees Celsius. Value when the pH value is appropriate. Calcium and magnesium exist in ionic form, facilitating chelation and removal by the resin. When pH is less than 8, the resin's ability to remove calcium and magnesium decreases significantly. When pH is greater than 11, magnesium ions easily form magnesium hydroxide colloidal precipitates, clogging resin pores and causing brine bias flow, leading to incomplete calcium and magnesium removal. Control range 9.0, 0.5. Brine flow rate determined by the resin tower selection and filling volume, depending on the tower size and required cycle time. Excessive flow rate results in short residence time of brine in the resin and easy short circuit, leading to excessive calcium and magnesium ions. Too small flow rate requires a larger resin tower. Control requirement: less than 40 cubic meters per hour. Optimal 20 cubic meters per hour. Calcium and magnesium ion concentration. The resin adsorption capacity increases with the increase of concentration, but when the mass concentration exceeds 10 mgl, the adsorption capacity decreases. The resin exchange capacity is fixed, and ions cannot be exchanged in time, leading to an increase in calcium and magnesium content in the secondary brine. Free chlorine has extremely strong oxidizing properties, easily damaging the resin structure and causing irreversible poisoning, leading to a sharp decline in resin performance and inability to chelate calcium and magnesium ions. Control requirement: no free chlorine in brine. 4. Control indicators for secondary brine purification, regardless of the 3-tower or 2-tower process. The quality control indicators of the secondary purified brine must meet the following requirements. In this lesson, We learned about the 3-tower and 2-tower process flows of secondary brine purification, the impact of process indicators on resin tower operation, and the quality control indicators of secondary purified brine. See you next time.